Alright, we're back with rotations again, and in this case, a second example of how to do moments of inertia with the integrals, and this time we'll do a disk. Same idea as we would have for sticks or anything else. We're going to use the integral version, which means we have to basically break up an object, a solid disk in this case, into a bunch of pieces. Pieces where we know how to find the inertias, and then the integral adds them all up to get the total. In this case, for a disk, the thing that we know how to find an inertia for, that would be a nice symmetric piece to break this into, would be a ring. So in blue, I'm drawing a thin ring around the axis of rotation, which is the center of the disk, and that ring has a certain radius. We'll call it little r, whereas the physical radius of the whole disk is big R. Okay, so it's nice and symmetric, and we know for a ring the inertia is just all of the mass of the ring is the same distance away. So in this case, the mass of that thin ring is just dm, and so we could say something like r squared dm. Okay. If you want the total inertia, we have to add up a whole bunch of these rings, all of different radii, different sizes, one after another, in order to get that total inertia. Okay. Now, the thing is, the variable. What is the variable? It's r. Different rings are going to have different radii, so it's one after another like this. We're going to be adding these things up from the center all the way out to the edge to fill in the entire disk with all these rings. Well, we run into a similar problem that we have for sticks. We have to figure out a way, how can you get, instead of dm, you have to get dr in there so you can evaluate this integral. So the geometry of this problem obviously is different than for a stick. Inertia is, we're talking about the distribution of mass. Well, the mass is distributed not along a stick, along a single length. It's distributed over and throughout the area of this disk that surrounds the axis of rotation. So instead of using a ratio of mass per unit length, we're going to use mass per unit area. So for the total disk, this ratio is the total mass of the disk over the total area of the disk, which would be pi big R squared. Now, we can make the claim that the ratio for one of these rings, one of the pieces, should be the same. So if we have a tiny little bit of mass, dm, distributed over the area of this ring, then we're in business. But how do you find the area of the ring? Well, let's see. I guess one way to think about this would be the ring has a little bit of thickness. A good calculus name for that would be dr. So imagine if you were to take that ring, cut it, and stretch it out into a rectangular shape. The area would have, we could find it with length times thickness. Okay, kind of like a rectangle. Well, the length of that ring is the circumference, 2 pi r, and the thickness is dr, so circumference times thickness would tell you what the area of that ring is. So with these ratios, this is how we can get dm in terms of dr. If we solve for dm, we will have a constant total mass over total area of the disk, times 2 pi r times dr. Okay, the pi's are going to drop out. And what are we left with? Total mass over big R squared times a factor of 2r dr. So this is what we have to put in for our dm in the integral. And let's see what happens when we do that. So we're integrating from the center out to the edge. We have this r squared. And now we substitute total mass over big R squared, 2r dr. Let's plot constants. 2 times mass over big R squared. And we're left with the integral of little r cubed dr. And when we evaluate this, let's see, the antiderivative is 1/4 r to the 4th, evaluated from 0 to r. 2 over 4 is a factor of a half. And we get big R to the 4th power. So lo and behold, we get this very famous and familiar answer that we've seen before, 1/2 mr squared. Okay, so that's when we have a disk which is spinning around its center. Again, we had to use an integral. It's a so-called rigid body. We broke it up into little pieces that we know how to find the inertias for. Key part is kind of right here. We're playing this game with these ratios in order to be able to evaluate the integral. But in the end, it works out, and we get the answer that we should have expected to get. So this one's definitely trickier than sticks, a little more involved, and I hope it kind of helps just to have another example of how these integrals work and how to set them up. And until next time, we will see you later.